Prove that a convergent sequence is a metric space is Cauchy's but not the converse. Now proof: let XD be a metric space and sequence Pn is a convergent sequence. In X, let Pn tends to P, let epsilon is greater than 0 be arbitrary by definition of convergence of a sequence. For epsilon is greater than 0, there exists a positive integers capital N such that the distance of Pn and P is less than epsilon upon 2 for all values of small n is greater than equal to n. Now we consider the two positive integers m and n is greater than or equal to n. Now dPn P is less than epsilon upon 2 and dPm and P is less than epsilon upon 2 for all values of n and m is greater than or equal to capital N. dPn Pm is less than equal to of dPn P and dP Pm is less than epsilon 2 plus epsilon upon 2 for all values of n and m is greater than capital N. That is d of Pn Pm is less than epsilon for all values of n and m greater than capital N. By definition of sequence Pn is a Cauchy sequence in X, hence every convergent sequence is a Cauchy sequence. Converse: the converse of the above result need not be true. We consider sequence 1 upon n, that is on open interval 0 1 close interval with metric 1 upon n is a Cauchy sequence. Let epsilon is greater than 0, putting n equal to 2 upon epsilon. We consider that n and m is greater than capital N. So d of 1 upon n and 1 upon m is equal to modulus of 1 upon n minus 1 upon m, which is less than equal to 1 upon n plus 1 upon m, which is less than equal to 1 upon capital N plus 1 upon capital N, which is less than epsilon upon 2 and epsilon upon 2. So that is d of 1 upon n and 1 upon m is less than epsilon for all values of n and m greater than capital N. So sequence 1 upon n is a Cauchy sequence. Sequence 1 upon n is not convergent. Now limit 1 upon n is 0 for 0 belongs to open interval 0 and 1 close interval. So sequence 1 upon n does not converge in 0 open interval 0 and 1 close interval, hence the Cauchy sequence may not be convergent.